Swayam Prabha. Digital India. Educated India.
Okay, so we have discussed what are various elements of a typical vibratory system, which we discussed as a damping element, a stiffness element, and which is a spring in a simpler sense, and there is an inertia element. So, each of these three elements are the main system elements, and the corresponding parameters like stiffness, damping coefficient, and the inertia or mass of the system, they are actually the main vibration system parameters. And typically in the process of converting a mechanical system into its vibratory model, we are all the time looking at which constitutes the inertia, which constitutes a dissipation element, and its associated parameter value, and what is the stiffness element in that. And most of the times, as we discussed, these coefficients, mass, stiffness, and damping, they are constant, and it has more important mathematical implication that the solution of such governing equation that we derive is simpler to obtain whenever these coefficients are constant, and that is the reason why we always given a choice and given the context treat these coefficients constant and get first cut solution, and that is what we always intend to. Now, what we are going to see and discuss are in which different ways the same system can be analyzed for different objective, and what are the different ways of vibration analysis. Ways, I mean, we can investigate the same system defined by this governing equation for its free vibration response. So, when it is done for free vibration response, the right hand side term, that is the forcing term, is assumed 0, and therefore, the equation turns out to be mx double dot plus cx dot plus kx equal to 0. So, that basically sets the ball rolling for free vibration analysis. Now, many times it is found that it is also convenient to obtain the free vibration response by neglecting damping in the system. Typically, mechanical system with structural elements where there is no explicit dashpot with fluid friction not present, then in that case damping indeed is of a lower order, and therefore, the vibration analysis can be done with Cx dot set to 0. So, so there are two ways in which this free vibration analysis is done. One is treating the system as undamped, or damping is not considered and is ignored. So, you have undamped free vibration analysis in this case done, wherein whereas if you include damping, then it becomes a damped free vibration. So, in that case the equation that you see here is what is investigated for damped free vibration, whereas when you have undamped free vibrations, then the damping term is ignored, and therefore, these equations respectively turns out to be this. Now, the first step of this undamped free vibration most of the times is to assess the natural frequencies, and the equation here is a classical eigenvalue analysis equation. So, the equation basically leads to eigenvalues in the system, and those eigenvalues are nothing but the natural frequencies. So, both of these two equations can be solved to obtain natural frequencies, and that is what we are interested in, and that is the reason the solution of this equation is the eigenvalue analysis. The other way is to retain the right hand side forcing term, and then you are essentially investigating the response, the vibratory response for forced excitation, and then the equation gives you the forced vibration response of the system. So, then of course, you retain the right hand side term and then analyze this equation or solve this equation for getting x of t, and the analysis is typically called as the dynamic response analysis. Now, you would think that since all our mechanical systems do have forcing function or excitation inherent, and without that, typically 90+% of your mechanical systems make no sense, or they do always have inherent forcing function, because all of them do have rotating elements, and then there will be always unbalanced excitation force. So, the question is, why do we really need a free vibration analysis or eigenvalue analysis? And obviously, you know that for us to ensure that the system works away from any possible resonance, we should in fact know the natural frequencies of the system. So, when we define the excitation function for our mechanical system, for example, the engine operating speed, we define what is this excitation function, maybe f cap cos omega t, and then in that case this omega is your excitation frequency. Now, once the rotational speed is fixed, to avoid resonance, obviously you would like to know what your omega n is, the natural frequency. So, when you want to ensure no resonance take place, the first prerequisite is to understand your system from the point of view of its natural frequency, and therefore, the eigenvalue analysis gives you an idea of all the natural frequencies the system can have, and that will help us to modify the parameters, or if possible ensure that the excitation function is away from that particular natural frequency. So, the first reason why we do eigenvalue analysis is to get the information about all your natural frequencies, because this is a general analysis process wherein it applies to multi degree of freedom system also, and therefore, the natural frequencies would be many in numbers. So, if you have 15 degrees of freedom, you have modeled that physical system, then you will have 15 natural frequencies. So, therefore, all natural frequencies are obtained through the eigenvalue analysis. Obviously, since we are beginning with a single degree of freedom system, the concept of mode shape does not arise here, but the second most important reason why we do eigenvalue analysis, as we shall see in 2 degree of freedom system later in the course, the understanding of mode shapes is important physically as well as more important mathematically, because we use these mode shapes for analysis purposes, and therefore, mode shape estimation is also an inherent important outcome of a typical eigenvalue analysis. In fact, when we do this eigenvalue analysis, you do get natural frequencies and corresponding mode shapes out of that process. We shall discuss mode shapes later, but since we have raised this question as to why at all we should do eigenvalue analysis, why do not we straight away go to forced vibration response and obtain x of t, is that for design approach, vibration based design, they have their own important implication or influence. The third thing that typically is mostly not discussed or considered, but is equally important for some mechanical system of course, is understanding of stability of the system. So, the third objective or outcome of eigenvalue analysis is to understand stability of the system. Typically for rotor bearing systems, the analysis for its stability is important, and eigenvalue analysis do turn up or do generate information as to whether the system is stable at different operating conditions, and therefore, stability analysis is also an important outcome of the eigenvalue analysis. Now, I will highlight a little bit of this part in the subsequent topic when we deal with damp free vibrations, and there it will be clear to you why the eigenvalue analysis is important from understanding of the stability of the system. Mode shape, of course, we will reserve this for later topic. When we deal with 2 degree of freedom system, we will get introduced to the concept of mode shape, but of course, all of you are quite okay and aware of why the natural frequency estimation is important. Okay. So, that is how this entire vibration analysis process can be done in variety of ways, and that is precisely is the topic here. We will begin with the free vibration analysis, and I shall now start the first activity on how to obtain a free vibration response of a mechanical system. So, solution of this simplest equation or governing equation of motion for a simple single degree of freedom system vibratory system. Okay. So, this is what we shall start now. So, the equation is mx double dot plus cx dot plus kx equal to f of t, in which we have gotten rid of the forcing function, the term on the right hand side. We have also removed the damping related term, the force term, and therefore, the equation that remains is an undamped vibratory system. I mean the governing equation is corresponding to undamped free vibrations. Now, why we call it as free? Because nobody is forcing it to vibrate. So, it will vibrate freely without being dictated by any external excitation function. Why it is undamped? Because you do not have a dissipating term in the governing equation. All right. So, then the question is, if nobody is forcing it, how will it vibrate? So, we shall look into that aspect. But if this is the governing equation, it will of course will have to be set in motion by some initial perturbation or initial disturbance. So, the whole objective in this exercise is going to be how x of t will evolve once it is perturbed at t is equal to 0. That is basically your initial conditions or initial excitation. So, how do you solve this? You have to assume a solution. So, typical process in the solution of these governing equations is to assume a solution for a 2 degree of freedom system, a second order ordinary differential equation. You all have learnt in your mathematics course that the standard form of a possible solution is a constant times e to the power s t. So, that basically is our assumed solution for this governing equation. We will cross check by substituting this assumed solution into the governing equation. So, we are basically assuming a solution. So, that is a typical standard process of assuming a solution and then substituting the assumed solution in the governing equation. So, when you substitute it, I hope all of you are familiar with all of these, if I want to find out the second derivative of x with time, this is what you will get it. And therefore, if I substitute both of these into this governing equation, I will get m a s square plus k into a, and then of course, e will e to the power s t is out common and equal to 0. In fact, a will also get out. Now, so if I take a out and e to the power s t out, essentially you get k into m s square equals 0. Now, this equation is valid at all times, and so therefore, you cannot have this term going to 0, and the arbitrary constant a can also not be 0, and obviously, if it is 0, then this solution is a trivial solution. So, for a non-trivial solution, the only way that this equation gets satisfied for all times is k plus m s square equals 0. Now, if that is the case, then s square I can write as minus k over m, and therefore, s is going to take, because this is a negative quantity. So, j square root of k over m, and of course, I will have two possible signs here, because if I square it, I will get this equation. So, because there are two possible values, I will say that there are two possible roots of this equation, and S1 and S2 corresponds to either of the two signs here, right. So, S1 is maybe minus j square root of k over m, and S2 is equal to plus j square root k over m. Now, this square root of k over m is typically called the natural frequency of the system. So, we define the natural frequency omega n as square root of k over m, and the two roots are plus and minus j omega n. So, the roots here of this equation are pure imaginary. There are two imaginary roots, and they point to a single natural frequency omega n. So, the roots are two in number for a single degree of freedom system. So, a 1 degree of freedom system, there are two roots which are imaginary, and there is only one natural frequency omega n. And if you extrapolate, it is it will be clear that if you have 2 degrees of freedom, there will be 4 roots, and there will be 2 natural frequencies, and so on, right. Okay. Now, if there are these two roots possible, then if I substitute these roots that I have obtained into the assumed solution, my general solution, because both roots are possible, I can then write the general solution of the governing equation as x of t equals a e to the power s1 t plus b e to the power s2 t. A and b are just arbitrary constants. So, do not confuse this a with this a. A and b are two new arbitrary constants. Okay. So, because both S1 and S2 are the roots of this governing equation, I can write the general solution as x of t equals a e to the power S1 t plus b e to the power S2 t, where a and b needs to be found as to understand how the total equation turns out to be. So, those are the unknowns that we would like to find. S1 and S2 are completely known now for a given vibratory system, because omega n is given in terms of the system parameters. Please make a note that it is equal to k square root of k over m, where k and m are the stiffness and mass properties of the system. So, they will be anyway known for a given system. Now, the question is, how do I find A and B, because unless I know both A and B, I cannot define my response at all instants of time t. Okay. So, therefore, I shall have to obtain A and B, and the way I can do that is by using some initial conditions, and that is what I will do, that I will make use of the initial conditions to find out the values of A and B. Now, the initial conditions for any vibratory system is the displacement and velocity at time t is equal to 0, that basically is your initial condition. So, x at t is equal to 0 and x dot, that is the velocity, at t is equal to 0. So, if I call this x at t is equal to 0 as x naught and x dot at t is equal to 0 as v naught as the two initial conditions at time t is equal to 0. We call it initial conditions because at time t is equal to 0, that is, those are the two impressed or given initial input to the system. Alright, so for doing that, I will obviously take the derivative of this general solution to obtain the equation for velocity, and then that gives me, of course, before I do that, I shall probably replace these A and B. So, S1 and S2. So, I have x of t to be written as maybe minus j omega n t plus b e to the power j omega n t. So, that basically is the general solution. Now, I can write x dot t as minus j a omega n. If I differentiate this with respect to time, I get this, and plus j b omega omega n e to the power j omega n t. Okay. So, this is basically the expression for velocity. All right. Now, as we have given initial conditions as x naught and v naught at t is equal to 0, if I prescribe these initial conditions, I can substitute for x by x naught and t by 0, and that is what I will do now. So, if I substitute into this equation, equation number 1, and this is my equation number 2. So, if I substitute 3 into 1 and 2, x at t is equal to 0 means x naught. Okay. So, we substitute into this equation the value of t by 0 and x of t as x at t is equal to 0, which is going to be x naught, okay, from here. So, then I have a, and what would be e to the power minus j omega n t? E to the power 0, that is 1. So, a plus b, right. So, when you substitute t is equal to 0 into this exponent exponential term, we get this as equal to 1, and then therefore, both this term and this term, both of them will be 1, and therefore, x naught is equal to a plus b simply. And then if I substitute for these initial conditions 3 into equation 2, x dot t is v naught at t is equal to 0. So, therefore, this is going to be, you can substitute t is equal to 0 in this equation, and x dot t at t is equal to 0 will be v naught, and therefore, I write this as v naught, and then what do you get here? J omega n into bracket b minus a, isn't it? This term goes to 1, this term goes to 1, and then this is what we are left with. So, then these are the two equations that we have after substituting initial conditions. Okay. So, let me call this as 4. Now, I will solve these two equations for A and B, because those are the only unknowns in equation 1 to define the free vibration response, because with right hand side equal to 0, x of t will define the free vibration response, but a system on its own will not start vibrating. You need to disturb or perturb it initially to let it vibrate on its own. That is what we are trying to find out. So, now if you solve these two equations, maybe I shall write this as V naught by j omega n, okay, equals b minus a, and maybe I will further slightly modify this term to write this as minus j V naught by omega n. Can I do that? If I multiply both numerator and denominator by j, I can get this equation. So, you basically get minus j V naught by omega n equals b minus a. Now, if I solve these two equations, then I will get a and b. Okay. So, if I add these two equations, then I get, so these two meaning these two equations. So, if I add both of them, then I get 2b equals x naught minus j V naught by omega n, okay, or b would be half of x naught minus j V naught by omega n. That is the expression for b that I have got here, and you substitute that into this equation, I am sure you will get a equals half, please do that yourself, x naught plus j V naught by omega n. Quite easy to do that. So, when you substitute b into this equation, you will get a as half of x naught plus j omega V naught by omega n. Do you observe something interesting in the expressions of a and b? What can you say about these two equations, expressions for a and b? Can we say that they are complex conjugates? So, the two constants a and b that you obtain here are complex conjugates, a minus j b and a minus j b. Okay. So, these two complex conjugates are obtained. Once you know these constants, your general solution is now a final solution, because there is nothing to be known and all the parameters are all known to you. Now, known in the sense, if I substitute for a, it is going to be half x naught plus j V naught over omega n e to the power minus j omega n t, and then plus half x naught minus j V naught over omega n e over j omega n t. Am I right? Because a and b are completely known in terms of course, the initial conditions that we will impose. Okay. It will be clear to you shortly how what actually x naught and V naught we mean physically. Okay. Obviously, these x naught and V naught are the initial conditions at t is equal to 0, after which those displacements are withdrawn. That means, they exist only at t is equal to 0. Subsequent motion of the vibratory system happens on its own. That is what we call as free vibration. Okay. Please make a note that everything will be known because x naught, v naught are impressed, they are already known. Omega n is also known because when you define your system, you have defined already what is k, what is m, and therefore, omega n is known. So, it is just a matter of solving this to obtain the expression for x at any instant of time. It is a function of an independent variable t. Okay. Now, having discussed this, let us go a little further, that this equation that we have got is a bit inconvenient to use actually, and it can be simplified to obtain a little more compact form. Okay. And for that we will make use of Euler's identity and get a better form of this particular equation, which is convenient to handle. Okay. What do you do? You multiply and try to get simplified version. Okay. What do you do? So, I have this equation already there. So, I will write it this way: x of t is for convenience sake to start with, maybe instead of using all of these, I will write this particular term as a plus j b just for the sake of convenience, and then this of course then becomes a minus j b, right. So, where a is x naught and b is v naught over omega n, just for convenience sake to get or derive the final expression. So, I or maybe this is x naught by half and this becomes half. So, I will take care of this half as well. So, essentially this equation I am writing here as a plus j b, and then you can write this e to the power minus j omega n t as what? Yes? Is not it? This is very well known. So, this is how I replace e to the power minus j omega n t by cos omega n t minus j sin omega n t, and then add to that the second term now turns out to be a minus j b cos omega n t plus j sin omega n t. Now, what do you get from here? You expand this, what you get is a cos omega n t and plus j b cos omega n t and then minus j a sin omega n t, and then that becomes plus b sin omega n t. You can try it yourself, plus the second term expands to a cos omega n t, right, and minus j b cos omega n t, and that gives you plus j a sin omega n t, and finally plus b sin omega n t, right. This one cancels out, that one cancels out, and then you are left with finally 2a cos omega n t plus 2b sin omega n t. And now I would replace these a and b, because now we have already assumed that a is going to be this and b is going to be this. So, I will replace a by x naught by 2, and that basically gives me x naught cos omega n t plus this 2b turns out to be v naught over omega n sin omega n t. That is your x of t. Now, this is much more convenient than the expression that we started with or obtained first, right. It is much more compact in the form. In fact, if you want to further simplify this or reduce this or write it in a different format, all of you are aware of what it actually is. A cos omega n t plus b sin omega n t is going to be square root of a square plus b square cos omega n t minus phi. So, I will do that exactly. So, I will write this same equation as x cos omega n t minus phi, and where x, the capital X, is nothing but square root of x naught square plus v naught by omega n square. Okay. And what is phi? The phase angle here, that is going to be tan inverse of v naught over omega n x naught. These are all standard mathematical manipulations. And I would like this phi to be called phi I, for the reason will be clear to you later. Okay. It just I would like to call this as phi I, and that phi I is actually initial phase lag. Okay. You will get to know what this initial phase lag is. X represents the amplitude with which the response is going to occur. So, it is going to have an amplitude of capital X, and the response, free vibration response, is going to happen harmonically, or it will vary with time harmonically because of the presence of this cosine term here, and it happens with the frequency of omega n. Okay. So, this equation tells us that the free vibration response of this simple single degree of freedom system is harmonic with frequency omega n with amplitude capital X, and what this capital X is, that capital X in terms of its value depends on which parameters? It depends upon the initial conditions x naught and v naught. Okay. So, the amplitude will be governed by the way you excite the system at t is equal to 0. Of course, it will depend on omega n because your natural frequency will be, of course, influence the your amplitude of vibration. Okay. So, this is how the response finally looks like, and we shall take couple of examples of how this equation looks like for different kinds of initial conditions or initial excitation or initial disturbance, right. Okay, we will take some examples of how do we model a vibratory system, and the example that I am going to take first is again this helicopter. Of course, this is too complex and too big a system to be modeled simply, but if we assume that as it lands on the surface, it is the landing gear that touches down first, and if suppose as a very simplistic model, vibratory model of this system during its touchdown process, if it is treated like a spring mass system, then the landing gear provides sort of a compliant supporting structure for it. So, I can treat this front landing gear to be a spring, another spring which is representing this particular landing gear at the back as well as this. So, there are actually 3 springs which are representing the landing gears of this helicopter mass. So, if I consider the entire helicopter mass as mass m here, and the springs at different locations, let us say this is K1 and this is K2, and maybe the 2 back landing gears, if they are assumed to have the same stiffness, maybe K2. This entire mass will then get supported by these 3 springs. Now, these three springs are obviously going to be in parallel. They are actually supporting the entire mass together, and you all might have studied in aerodynamics and kinematics of machinery on the first preliminary discussion on vibration theory, that the springs, if they are in parallel, they can be clubbed together as an equivalent effective spring, and that equivalent spring, if I denote as Ke, then for springs in parallel, this Ke is going to be summation of all the spring stiffnesses. So, it will be K1 plus K2 plus K2. So, that is 2 K2. You simply have to add the springs if they are in parallel, right. So, now if you have a quantified value of all of these suspension parameters, you can actually define what is the spring on which the helicopter will be supported as it lands on the surface. So, then this becomes a simple single degree of freedom system, provided we only consider the vertical motion of this mass, and then the natural frequency of this system can be calculated, which is of course going to be discussed, that if it lands with a certain velocity, how to find out the vibration response. But the natural vibration frequency of this particular system can be evaluated based on these parameters. So, this is one of the very simple way in which you can model it. Of course, there is an implicit assumption here that the mass is centrally located with respect to all the springs, and then if the mass is offset, suppose if the helicopter is represented like this, then the front spring and the rear springs, if they are modeled like these, then you can also have, apart from the vertical vibratory motion, a pitch motion. So, apart from x, you can also have a tilt vibratory motion for this helicopter, and then you can also find out the governing equation of motion, but that part of course we are going to learn in a 2 degree of freedom system discussions, and in the initial part we are only going to focus on a single degree of freedom model. Okay. So, this is how I can model the system using springs in parallel in this particular case. The other example that I might like to take in this case is an overhead travelling crane, as you see here, which are typically used in all workshops and in moving heavy equipment. Now, what is this entire vibratory system here? This overhead travelling crane can be considered to be a beam supported at its ends here, right. So, these are the end supports on the railings here, and this particular yellow colored girder that you see is the horizontal beam, and that carries an equipment which is like a winch or a pulley system, which tries to lift and transfer the weight, as you are noticing here. So, this is sort of a mass that you may imagine here being transported from one place to another. If we assume that this particular pulling structure, or a structure that lifts and lowers the weight, that pulley structure, if we assume to be comparatively lesser mass as compared to the mass being lifted, then I may like to model this entire system as a single degree of freedom system. Okay. Now, how do I model this as a single degree of freedom system? The wire rope here, what you notice, itself can act like a spring, because the wire is not absolute rigid one, and under the action of such a heavy load it can stretch, and that stretching means that it is a compliant member, has and may have certain stiffness. So, if I assume the rope to have a stiffness given by a variable Kr, and if this girder is assumed like a simply supported beams, I can now treat the stiffness of this beam defined by a spring. Okay. The spring basically defines now the stiffness of the beam, and I will treat or call this as Kb. So, if the force gets applied here, this beam might deflect like this, and the mass will of course deflect, and it might further deflect because of the deflection in the rope. Okay. So, I have one stiffness here, that of the beam, and then another stiffness which is the stiffness of the rope, which will carry the mass ultimately at the end. Okay. So, this as a simplistic approximation of this entire system. Now, you may notice that the springs in this case are in series rather than in parallel, compared to the previous case. These two springs will now be in series, and kindly refer to all your earlier discussion on the springs in series, effective spring stiffness. So, if I model this as a simple spring mass system, the effective stiffness of this entire system is going to be clubbing these two springs in series, and that is possible by writing the expression for effective stiffness to be Kb 1 over Kb plus 1 over Kr is equal to 1 over Ke. So, effective spring stiffness in such case will be given by this. So, if you want to find out what is the effective stiffness, that effective stiffness is going to be Kb Kr divided by Kb plus Kr. This is how these springs are to be added in series and in parallel, and once you do that, the rest of the process is quite straightforward. We all know that for a spring mass system, the natural frequency is given by K over m, and if you have this kind of a simplified approximate model of the system, you can quickly get an idea about what could be the natural frequency of the system. Okay. All right. Now, many times it so happens that we may have to simplify the modeling process, and looking at the girder, if suppose this Kb, the stiffness of the girder turns out to be 100, just a hypothetical case, these numbers are not that important, but I am basically trying to highlight the modeling approximations. Okay. So, these numbers may not be realistic for this particular case, but the relative values could be realistic. For example, if the rope stiffness turns out to be just 10 Newton per meter, and in comparison the girder stiffness turns out to be 100 Newton per meter, and the mass being lifted, again not so realistic value, but they are going to be relatively similar to the actual case. So, mass may be 500 kgs, and then the girder stiffness will be a couple of orders of magnitude more, but what is important is to let you understand how we simplify the modeling process. Okay. So, if the stiffness differ by such a large value, it might be more appropriate to consider the girder to be almost rigid, and then you may consider the stiffness of the rope only to consider or find out the natural frequency of this entire vibratory system. Okay. And that would be numerically easier to see here, that the effective stiffness, even if you consider such a large differing stiffness values, this product is going to be 100 multiplied by 10, and this is divided by 110. So, this is approximately equal to let us say 9.1 or so, yeah, roughly 9.1, and if you find out the natural frequency from this equivalent stiffness, this is going to be 9.1 divided by 1. So, this is going to be approximately 3 point something, okay, 3.0 something. And if you make a simplifying assumption saying that since this kb is too stiff compared to the rope stiffness, then I will only consider the rope stiffness, assuming that this entire girder which I earlier assumed to be with some spring. So, it all assumed like a rigid element, and then if I find out the natural frequency from this approximation, then it is going to be square root of what, k r, which is going to be 10 Newton per meter, divided by m, which is 1, and this is going to be 3.1 something, right. So, what basically we are saying is that the natural frequency that you obtain by simplifying the model, particularly when there are such a large difference in the values of two springs, is justified, and the amount of error that you will get. So, this also is in radians per second, I am sorry. So, that you can see that 3.1 and 3.0 something would be like hardly any difference in the values estimated. So, if you are wanting to know approximate value of the natural frequency, these kind of simplifying assumptions are always made, okay, which should justify in the process of approximations. Okay, the final example that we may consider here is that of a wind turbine system that we earlier talked about. Now, again, if I want to model this as a simple single degree of freedom system, supposing that this is a vertical longitudinal vibration problem, this column would again be modeled like a spring, isn't it. So, if it is modeled like a spring having some stiffness, the mass of the nacelle sitting at the top, if this is like a longitudinal vibration problem, then the stiffness has to be appropriately calculated. Now, that of course will depend upon the material properties and the shape and size of this particular column. Assuming the column to be a circular one, then we all know that if we apply a force, right, if you apply a force on such a circular straight constant cross section bar, the corresponding deflection can be obtained, and from your solid mechanics strength of materials, the relationship between this F and X is given by AE over L. Okay. So, the deflection due to force F is given by this, and therefore, the stiffness of this spring will be obtained as AE over L. A is the cross sectional area of this bar, in this case the column, E is the Young's modulus or elastic modulus, that is what we call it in newtons per square meter. A is the cross sectional area of that bar in square meters, and length of this particular column, that is the length, okay, in meters, all in consistent units. Then the stiffness will be given in newtons per meter, and then based on this you can find out again the natural frequency in the vertical longitudinal direction. But as we discussed that this mass is going to be subjected to twisting moments, and then due to the rotation of the blades, the unbalance can create a twisting moment at the tip of this column, and this beam in the vertical orientation will be subjected to a twisting moment T, and then we would like to know what is, if I define this as a torsional vibratory system, where this mass will now be considered as inertia, because now it is going to be an angular rotational motion, vibratory motion of the nacelle, and so angle theta will be the vibratory displacement, and what is going to resist that motion about the vertical axis is the torsional stiffness of this column. Okay. Now, so basically the governing equation of motion mx double dot plus kx equal to 0, the free vibration governing equation of motion will now change so that governing equation of motion will now change to I theta double dot plus kt into theta equal to 0. Okay. You can show that the way we use Newton's second law for getting the governing equation of motion. On similar lines for a torsional vibratory system, you can get that system of the governing equation to be this. And now the natural frequency is going to be kt over I, where I is the mass moment of inertia of the nacelle or the mass sitting at the top. Now, how do I quantify the value of torsional stiffness? Okay. It is obviously going to be force by displacement, which in this particular case is going to be the twisting moment divided by the twist, the angle of twist in radians, and we have the relationship again from the strength of materials that T over IP is equal to g theta over L, and we want this stiffness to be calculated. So, from this relation I can have kt value, okay, which is going to be T by theta rearranged to g IP over L, and we know that for a circular cross section this is pi over 32 d to the power 4, where d is the diameter of the rod, in this case the column. So, and g of course we all know that it is a shear modulus given in Newton per square meter. IP will be of course in the units of meter to the power 4, and this is how you will get the value of kt, and that will come out to be in the units of Newton meter per radian. Okay. So, once you substitute the numeric value of kt, which you can find out if you know the length of the column, if you know the cross sectional dimensions and the material properties such as shear modulus, then you can find out the natural frequency in torsion for this particular case. The same system now vibrates in torsion. And of course, in the bending case, if you treat this to be a vertical beam subjected to a lateral vibration having a tip mass m, the stiffness here of the beam is going to be kb. Now, kb from again going back to your strength of materials, if a beam, if the beam is having a concentrated end mass or end force, the deflection is given by 3 EI over L cube into P or into F, sorry, F is given equal to 3 EI by L cube into delta, and delta is this deflection in the beam at the tip where the force F is acting. So, essentially this will give us the stiffness of the beam in the lateral direction as 3 EI over L cube. Okay. And so, in this case if you substitute for kb in the governing in the equation of motion, considering this to be again a spring and a mass system, then the natural frequency kb over m will give you the natural frequency in the bending vibration. So, this is the case of a bending vibration. So, in all of these cases you can use your understanding of solid mechanics to get the relative relevant expressions evaluating the numeric value of the stiffness involved, and apply the governing equations to find out the natural frequencies. These are some of the examples I thought I would like to take before we move on. Another example here, how do I model this system as a vibratory system? A diver is jumping off a springboard. So, if the driver is there are interesting things here. If the driver is standing at the tip of this springboard, the diver is going to have his own mass contributing to the system, and then assuming the mass of the diver to be substantially large compared to the mass of the springboard, I can treat this to be a cantilever beam with an end mass and then calculate the natural frequency based on that. So, you all have seen in the previous slide how I can calculate the Kb value and use the mass of the diver to find out the natural frequency of the system. But if the diver jumps off from the springboard, then the springboard is without any mass, okay, and I need to approximate this to be again a spring mass system. Okay. So, then what I do is, you will find that also we will discuss that part again in the subsequent classes, that for such systems I can approximate this mass at the tip to be equal to 1/3 of the mass of the springboard, okay, and K will still be the same. So, K is the stiffness of this cantilevered beam, and once I find out this the value of the bending stiffness of this beam, treating it to be a cantilever using all the dimensional properties of the springboard and the material properties, I can find out the natural frequency of the springboard alone without the diver. That will be different than the natural frequency when the diver was still standing at the tip of this cantilever. Okay. So, using this, the natural frequency can be obtained as Kb 1/3 times the mass of the board. So, based on the material properties of the board, you can find out the mass, okay, and this is going to be how the natural frequency can be calculated. If you really look at closely, this particular board is actually fulcrumed at these 2 points. So, as it's an interesting case here, that if it's fulcrumed here and the edge here is just supporting this, then what happens is the system is like this, that you have the board fulcrumed here, but there is one support which is here, okay, and then the board, while it deflects downwards, has an effective length given by this, all right, and when it swings up and it goes beyond this equilibrium position, this particular deflection will be fulcrumed around this, because if it goes up and loses contact with this particular support, which appears to be the case here, then it is going to have an effective length in the upper half of its rotation or vibration, something different than what it is here. Okay. So, then because your Kb is what, that the bending stiffness of the cantilever is 3 EI over L cube, of course, with the assumption that the mass of the board is assumed concentrated at the tip, and that mass we have approximated to be 1/3 of the total mass of the board, then this Kb is the stiffness that you can calculate, and then in this case you can see that it depends upon the length of the beam. So, the stiffness in one half of the oscillation vibratory displacement, in one half the stiffness is going to be different, in the other half the stiffness is going to be different. Okay. Then the system is not really a linear vibratory system, it is going to be a bilinear vibratory system. In one half of the oscillation cycle, the stiffness is different, and the other half the stiffness is different. But why they are bilinear? Because in one cycle there are only 2 possible values of the stiffnesses. So, if you really see F versus deflection, then it will follow one stiffness value, and in the next set of half motion, it may have a different stiffness, you know. Yeah. So, it is called as the case of a bilinear stiffness. Anyway, but we will not get into the details of that. This, if we assume that it is going to, you know, rock around this particular point without releasing the contact point here, then with that assumption you can still find out the natural frequency of vibration of this particular springboard. Okay. So, this is how we can model this specific system. Now, we take another example here where the spring, let us say, is given by stiffness K1, this spring is of the stiffness K2, there is a mass which is shown here, there is a rigid link here, this is a rigid link which is having a joint with a rod which is an extension of this mass, and this rigid link is fulcrumed at this particular point. So, it is fulcrumed here, let this length be A and this length be B, and the mass moment of inertia of this link, rigid link, is given by I. Okay. We would like to model this and get the governing equation of motion for such a system. Now, if you look at the system closely, it is kind of a mechanism which can be used in practice. The link actually rocks, okay, and about this fulcrum, and so obviously this could be one of the degree of freedom that will be there for this system. So, theta, the angular displacement of this rigid link about the fulcrum, if it is theta, that is our degree of freedom. Now, this mass is going to, for small amplitude of vibration, the displacement x is going to be associated with this mass, but I am sure you will agree that if it is a rigid link connecting the mass to the vertical link here, then x cannot be an independent degree of freedom, because depending upon the angle theta, this link is or this joint is going to move laterally by a distance which is going to be is going to be given by A into theta. A is this length. Okay. So, x is not independent, it is dependent, directly related to theta, okay, because the link assumed is rigid. So, there is no deflection taking place. So, even if mass is going to move with certain translatory motion here x, for small amplitude assumption theta is small enough, we can approximate x to be equal to A into theta, and therefore, you can see that the number of degrees of freedom is only one, and that is theta, the angle of oscillation of the rigid link. Okay. Now, if that is the case, let us look at what are the forces which are going to act on various elements here. Okay. So, we may consider this link which is fulcrumed here. Okay. What is the assumed degree of freedom? That is our rocking motion, the theta angular degree of freedom, and then there is a mass which is since this link is also rigid, you can assume that the mass is sitting here, and then the mass moves along with the link, right, and then there is a spring which is connected here. So, if I consider this to be a free body diagram, then on this mass and the end of the link, if the theta is considered counterclockwise positive as have been shown here, then the spring is going to pull the mass back to its original equilibrium position, and obviously the displacement x which is going to be here being x theta, then what is going to be the restoring force? The restoring force is going to be, if the mass here moves on the leftward direction like this, there is going to be an additional stretch in the spring which is given by this value. Okay. And how much that value be? That value is going to be A into theta, because if theta is the angular oscillation at any instant of time, then A into theta is the translatory displacement of the mass, okay, from its original equilibrium position. So, if theta is swinging on the in the counterclockwise sense, the mass is going to move leftwards and the spring is going to get stretched by this distance, and then that stretch in the spring A theta multiplied by k is going to be the force which is going to pull the mass back to its original equilibrium position. While this is happening, while this theta is happening in the clockwise counterclockwise sense, the spring which is attached at the other end of this link, that also is going to stretch. So, if this link swings, the additional deflection in the spring that is going to happen is now going to be into theta, where b is the distance from here to here at the contact point. So, the stretch here is going to be the b theta, and that stretch is going to cause the spring k1 to restore it to the original position. So, k1 into b theta is going to be the restoring force acting because of this spring at this end of the link. Now, if these are the forces which are going to act on this free body, then I can now start looking at application of Newton's law to this system, and for that I need to write this in the coordinate system that I have used, which is basically showing that theta, the angular motion about the fulcrum as the degree of freedom, then the mass moment of inertia of this link and associated elements times the angular acceleration is equal to summation of all the moments which are acting about this fulcrum. So, if it is about fulcrum O, then all the moments about this fulcrum O in the direction of the angular acceleration is something which shall give me the equation of motion. But what is I? I is the mass moment of inertia about this fulcrum. Okay. Now, what this I will be? I will be that of the link itself. So, if I call this as I L, the mass moment of inertia I L, but there is a point mass, a rigid mass which is at the tip of this link, which is at a distance A from this. So, I can add that inertia, and so I am going to write this as m a square, and then this now becomes the total inertia, angular inertia, rotational inertia about the fulcrum that I need to account for. So, if you know the mass moment of inertia of the link and the mass value of this point mass, I can find out the total inertia value. And so, I theta double dot will be equal to what? All the summation of the moments. Now, what are the moments? One moment is of course going to be due to this force, the force which is which the spring K2 is going to exert on the mass, and so the moment of that about O is going to be the force times the distance or the arm length, which is going to be A, and this is going to act in the direction which is opposite to the angular acceleration. So, therefore, this angular acceleration is assumed counterclockwise positive, whereas the moment generated by A theta k2 is going to be clockwise. So, this total moment is going to be minus A theta k2 into A, and on similar lines this moment due to the force k1 b theta is also clockwise. So, I am going to write this force multiplied by the arm length, this is going to be B, and that is going to be multiplied by B. So, if I simplify this, this is going to look like I theta double dot plus K2 A square plus K1 B square into theta equal to 0. That is going to be the governing equation of motion for this particular system, and obviously this is in the form mx double dot plus kx equal to 0, and we know that that gives us the natural frequency of square root of k over m. And on similar lines, if this is the governing equation of motion, then the corresponding natural frequency in the angular motion of this particular linkage is going to be square root of k2 a square plus k1 b square over I, where I is given by this value. Okay. So, that basically now becomes the governing equation of motion for this vibratory system. That is how one can find out the governing equation and natural frequency by the Newton's law, I mean Newton's approach, the figuring out what are the forces acting on the free body. Okay, the vibration response can be in the units of displacement, velocity or acceleration. In these three forms, the vibration response will get generated, in the sense that when you solve the governing equation of motion, mx double dot plus cx dot plus kx equal to, let us say, f of t, ultimately solving this equation you will generate what is the response, and that response obviously is in the displacement unit. So, maybe in standard units we may get this response in meters, although in all practical purposes mechanical vibrations will be in millimeters, or in fact in microns in many cases, right. So, but if you really look at the practical vibrations and the measurement of vibrations on mechanical systems, the sensors which are typically used will generate response in acceleration unit. So, we need to know how are they related actually. Okay. So, the response or vibration in acceleration would of course the unit will be meters per square second, and in practice many times instead of meter per square second the unit used is G unit. Okay. So, basically it actually means that if you have 9.81 meters per square second of acceleration value, then that is treated as 1 g of acceleration obviously, right. So, you should be able to convert the acceleration into from meters per square second units to g units by simply dividing it by 9.81. Now, there is obviously a relationship between displacement, velocity and acceleration. We all know that we write x of t typically as x cos omega t. This is what we are seeing this response as, the x of t is x cos omega t, where x actually is the amplitude of vibration, right. So, this is your amplitude of vibration, and the cos omega t is the harmonic time function, which actually means that the vibration value of instantaneous response x is going to be changing from a maximum value of x through 0 to minus x and then back to plus x. So, in a cycle. Now, obviously, if you differentiate this with respect to time, particularly if your vibration is a harmonic vibration in the sense that it has only one frequency involved, then the time derivative of x, if you differentiate it with respect to time, you obviously will get minus x omega sin omega t. Okay. Then the velocity here is related to displacement through this value minus omega times x sin omega t, I can write as cos omega t minus pi by 2. Okay. So, the amplitude, if you really see, the amplitude is going to be omega times x. The displacement amplitude and velocity amplitudes are related through omega. So, if x is the displacement amplitude, then velocity is going to be omega times x, and on similar lines you can show that further differentiation x double dot or acceleration in the is going to be minus omega square into x cos omega t. Okay. So, which actually means that omega square times x is going to be the acceleration amplitude. I am dropping negative sign for the simple reason that the velocity is going to vary like this. So, when the displacement is 0, velocity has negative maximum value and it is going to be like this. Okay. So, it just if you really focus only on the amplitude value, the amplitude value is going to be omega times the displacement amplitude, and similarly acceleration is going to be starting from here. It will have certain negative value, and then it will have again a harmonic variation in its value as a function of time. But most important part that you should understand is acceleration is omega square times the displacement amplitude, and velocity amplitude will be omega times the displacement amplitude. That is how they are related. Okay. The units of velocity response is obviously going to be standard units is meters per second, but in practice the velocity based measurements are typically recorded in the units of millimeter per second. The displacement can have any value, any unit as such, many times for small level of vibrations micrometer is the displacement unit, because typical mechanical vibrations will not go beyond a millimeter value. Okay. So, just to give you an example, our power plant rotors, the steam turbine rotors typically will not have vibratory motion exceeding maybe about 50 microns or so. If it goes beyond 150 microns, the turbine is supposed to trip, and it is designed to trip when the values of the lateral vibration amplitude goes beyond 100 microns, depending upon the capacity and the unit. Okay. So, typical vibratory displacements would be in micrometers, seldom in many cases it will exceed a millimeter value. Of course, there are certain cases or certain applications where the amplitude of vibration will go beyond a millimeter level. Velocity units, as I said, practical vibration measurement units are millimeter per second, but standard SI unit for that will be meter per second. Acceleration, as I said, meters per square second is the unit, but G units or G level of vibration is a practical another alternate practical unit people use, and you should be aware of this relationship of the unit conversion. Incidentally, the reason why accelerometers are used for high frequency measurements is all because when your vibrations are at very high frequency. So, if I show the acceleration plot, higher frequencies actually show a very large vibration amplitude. So, the response at very high frequencies in terms of acceleration unit will have a very large amplitude. The same measurement or same mechanical system, if you use displacement sensor, the displacement sensor will hardly show any amplitude here, and that is because the vibratory displacement, even if they are very small in amplitude, the very fact that acceleration is omega square times x means that very large value of the frequency. For example, if we are talking about 4 kilohertz or 3 kilohertz of frequency involved, multiplied by 2 pi, that gives you radians per second. So much of squared magnitude value is going to get multiplied by the small displacement amplitude, and that is how the acceleration signal in high frequency range will show up much stronger, much larger amplitude, and that helps us in detecting such high frequency components in the vibration signal. So, high frequency vibration measurements are always made with using accelerometers, which generate the vibration response in acceleration units, and the reason for that is this, that acceleration response is the fact that it is omega square x, x is limited at very high frequencies, and therefore, small amplitude vibration components may not show up properly, they are not noticed in a displacement vibration response. So, whenever measurements are for very small frequency range, maybe less than about 50 or 100 hertz, displacement is the unit of measurement. When high frequency measurements involved are involved, the de facto choice then becomes the accelerometer, and acceleration data is commonly used. So, this is how one should have a basic understanding of the relationship between displacement, velocity and acceleration. Of course, this pertains to harmonic signal, but individually each frequency can still be converted using these expressions that we discussed. Okay, in this lecture we looked at the importance of eigenvalue analysis when we carry it out on a vibratory system. Then we solved our basic governing equation of motion without any external excitation. The free undamped vibrations were analyzed, and we saw how the initial conditions are accounted for in getting the response expression for a simple single degree of freedom system.